Hi, welcome back to Missing Chemistry. This is electron configuration of Samarium, SM was it. Okay, so Samarium is atomic number 62. It is element 62 in the periodic table. And its atomic mass unit, or AMU, is 150. Okay, since the atomic number is 62, the number of protons must be 62. And since it's electrically neutral, it would also have to be 62 electrons. Now the number of neutrons, okay, so that's the AMU minus the number of protons equals our neutrons, okay? So that would be 150 minus 62 equals, that would be 88 neutrons. So we're going to put 88 right there. Pretty darn snarly. Okay, so let's clean this up a bit here. And let's get back to business. Okay, now, so we have 62 electrons. That's the only thing that we're really concerned about. Remember that S has 2 electrons, P can hold 6 electrons, D can hold 10 electrons, and F can hold 14 electrons. We're going to use the off-ball principle, saying that we're going to fill in the lower electrons to the lower shells first before we fill in the upper shells. And we're going to follow something called the diagonal rule. So we're going to start right here in this diagonal rule right here. And we're going to keep on going until we run out of electrons. So we got 1s2, and X here, 2s2, and you're just sliding down the slide, 2p6, 3s2, 3p6, 4s2, 3b10, 4p6, 5s2, 4d10, 5p6, 6s2, and then 4f6. If you add all that up together, you will get 62 electrons. Okay, so let's do Hund's rule, which is orbital notation. In Hund's rule, you have to put an up arrow in every suborbit before we start the down arrow of that suborbit. And then until we do that until we run out of electrons. Pretty darn simple, huh? Up and down, see that? Up and down. Now watch this, 2px, 2py, 2pz. Hund's rule says you have to put an up orbit in every suborbit. There you go. And then you can start the down arrows. Pretty darn amazing. 3s. Yeah, see how that works? It's pretty simple. It's not a lot of rocket science, guys. Okay, look at that. Look how easy that is. I'm just going to keep on going until I run out of electrons. Remember that you have 62 electrons, which is what you get up there. Pretty simple. I'm liking it. Up to 5p6 now, guys. We're getting close to being done. Then we're going to do 6 of these out of the possible 7 of them. Okay, and we're going to stop right there. So there's 6 arrows going up. Now, let's do our noble gas notation. Now, noble gas notation is like a shortcut. So we kind of like, you know, when you're writing something, if you had shorthand, you could like condense a bunch of words down to just a few words and do the same thing. So xenon is our nearest noble gas. Xenon ends in 5p6, so let's go ahead and show you something here. So when we do this, we're going to cut all of this out. This is what noble gas notation is all about. See that? All that xenon. So we're going to put XE inside this bracket here. Now all that remains is this. So we're going to put this in numerical order. 4F66S2. Pretty darn snarly, I'd say. Okay, now what about our quantum notation? Okay, well, we know that's in the F block, and the F block has n-2, and it looks like it's in group, or period 6 actually, so you go 6 minus 2, so in reality it's really period 4. So the n value is 4. The L value, since it's in the F block, the value is 3. Then you go minus 3, minus 2, minus 1, 0, 1, and we start counting it over. It's going to be 2 on the count over for the n. And that last arrow right there is going up, so it's going to be 1/2 positive. And that's it for this lesson. You guys be snarly, and we'll see you back here at Musin Chemistry!